Okay, hello students. Completed one problem yesterday on helical gas. Continuing today, also the helical gas second numerical. I'll show one question. I'll show the question once again. Yeah, this is a question which we started yesterday. The question which we started yesterday, a typical question similar to Spurgear. Okay, so only difference is in the formula which we use. So I hope everyone are following up with yesterday's question. This is the question. So yesterday we just started off with the data. Power was given, the RPM, and velocity ratio, number of teeth on pinion was given, and pinion and gear were two different materials, and the normal angle, there is a angle for the formative teeth. Normal always means the formative teeth. That was given 14.5 degrees, and beta is 25. Beta is the helix angle. Okay, so this much was given. So in step 1, we were assigned with identifying the weaker member and allowable stress from the table for materials. We noted two different allowable stresses and the Y, which is the form factor. So we use the form factor as 20 degree full depth involute, and we substituted the values for Y1 and also found N2, Z2, that is number of teeth, okay, and Y2. So Y2 is again the form factor, the Lewis form factor. So based on this formula here will give us which is the weaker member. Just multiplying the multiplying here with the allowable stress to the form factor. That's how you find the weaker member. So once we're done with that, we found here that the gear, the product of those two were lesser in gear. So therefore, gear is a weaker member, and design should be based on gear, meaning all whatever parameters we take henceforth should be of the gear, okay, with subscript 2. So that's why in the velocity we have noted that D2 over here, okay, D2 N2. In all the previous problems on spur gear, you can see that we usually noted the value of 1, that is for pinion. Pinion one is usually the weaker member, but here you got gear. That is the importance of the first step. Okay, so here we're writing in terms of normal module. Also, the small change you need to make in terms of when solving for helical gears. Okay, this ZMN, so use it for the normal module MN. Okay, so make sure you put that subscript as MN, which is a normal module. So this is by default for helical gas. So part 1 we got FT to be this much over mn. There is the normal module. So normal means we are designing the spur gear. Spur gear means the virtual or the formative gear, which I spoke about in the first lecture, the introductory lecture for helical gear. Okay. So normal always means that it is the for the spur gear or the formative spur gear. Okay. Okay. So ft is different. This is a Lewis equation for tangential tooth load. It is different than the one which we use for spur gear. You can see in the presentation here. Okay. So this is the one. This is the part, the second part. This equation. So this equation is given for helical gears. The wear factor is extra along with the uh, velocity factor. You will find one more factor which is extra, and you need to substitute. See, one by one, it is given right below the formula. You can note down the values. Okay, so we'll go back. CW. So Y is given. Only thing is we need to calculate that, and sigma D is known as we are using D2 in this case, and CW. So let's take this sigma. I will find one by one according to this flow. Yes. Okay, CV. CV, that is the velocity factor. Velocity factor. We'll go back to the PPT. Okay, we are getting CW here. So we'll take it off from here itself. So CW is enclosed, continuously lubricated with oil and proper viscosity and characteristics. Scant lubrication material. So this data is not given in the question. You are free to choose your own value here, but you need to read the question carefully before choosing the particular value. So since here it is not given, we are assuming. Let me assume the first one, 1.15 for the wear factor. Since it is not given, let's change this to W 1.15. This is assuming, and from table 12.21. Then I am assuming. Okay, so we have then CV. Okay, we'll take off CV now. So let's go back to the PPT, see what this is. Okay, next is CV only. So CV, we don't have the velocity yet again. Okay, CV is not known. Okay, because the velocity is not known. No, so velocity value, exact value of velocity is not known here. So velocity we have in terms of this 1.15 into m. Okay, but this we are not sure on the velocity. So here also we have the freedom to assume one of these three formulae. So either 5 meter per second, 10.5. So let's choose the intermediate one. Okay, you are free to choose any of the three. Okay. So CV, let's say we'll take this value equal to 6.1 over 6.1 plus this value here. This is V. So V, okay, let's write V. So this is equation 12.25B. 12.25. Okay. So let's substitute this. Velocity, I think we already have velocity. So you can use that. So velocity here is 1.51 mn. 1.51. Let's copy this. Right. So this is our CV. Then what about next? Go back to PPT. Okay. After that we have B. So value of B here. Okay. Value of B. Let's choose from this equation here. Okay. So here also the intermediate one, or we can take the last one also. We'll take the last one. So as a common practice, let's take the last one here. So 12.23C, this last value. So B is lesser than or equal to 20 mn over sine theta. We'll use this value here. Okay, so B equals C fraction 20 mn over sine beta. Okay, so this needs to be calculated. So let's calculate. I think we have all the values. We have sigma d, we have CV, we have B, then Y is here, Mn as usual, CW. Okay, we have all the values. So let's calculate this one by one. So Y, capital Y is pi times Y. So pi times 0.141 is 0.443. Then this here. So this is equal to, this cannot be simplified. So let it be like this one. What about this? 20 over sine beta. What is beta? Beta, I think 25 degrees. Beta is 25 degrees. So sine 25 is 47.32 and mn. Okay, so this is simplified. So let's all put this in this equation here. Okay, so this is equal to, we have sigma d initially. Sigma d is 138.3 into CV, or CV, need to put this entire thing here. So let's put this entire thing here. That won't work. About this. We'll put it at the last. This into this whole value. So that is your CV. Then B. So B is this value here. Into B into Y. So Y also we have found to be the 0.443 into Mn as it is. So CW we have chosen already 1.15, right? So all these values are ready. Okay, so this is ready for calculation now. We will equalize. So now for part one, part A, we had already solved a little bit. The tangential tooth load part, we had already solved a little bit. So we'll take this part, copy this, and that's nothing but ft. We'll put it here. Now this equal to, we'll write a simplified version of this equation here. Okay, let's see how that looks like. So it is 138.3 times 4732.443 to 6.1. You can calculate parallel to what I'm doing. You can do it and tell me if I'm doing any mistake of any sort. So this answer I can divide by 1.15. So that gives me 15378.1 over, this is still 6.1 plus 1.51 and ml. Okay, and it is also mn here because we have many 1, 2. To have 2 over here, we can put this as a square value over here, right? So that will do. Simplifying further this equation, let's simplify this. So this is 11920.53 times 6.1 gives us 72715.2.3. 7252 5.2 times over here, I think. Okay, plus 11920.53 into 1.51 is around 18,000 into mn is equal to, we get 15378.1 to mn cubes, cubes itself. So this is 3. Okay, so this mn goes here, it becomes mn cube, and these both get multiplied with this value, and it becomes in this manner. So now if we solve this in an equation, so what do we get? Let me put this in an order so that you can visualize what's happening in the calculator. This is minus of this, and again minus of 72715.2 equal to 0. So solve this in the calculator. Tell me what is the value of mn. You guys are solving in the calculator. Have some practice solving in the calculator. And tell me what is mn. In the meantime, I'll go to the next step. Okay, so next step, step 3. Step 3 is to find the tooth parameters. Find the helical, right? Helical care parameters. If you check out the presentation, so if you see this this particular slide here for step 3, he has told you that spur gear and helical gear, you can use the same module. What do you get? So same module you can utilize in finding these. Okay, so in this last column you can use the value of mn itself. You don't need to separately define for that, or no need to find m. You can directly use the value of module in finding the care2 parameters. Right. Let's get back. Anybody found out mn? Let me check it out. Third degree is 15378.1. B is 0. C is minus 18000, and D minus 72715.2. Getting somewhere around 1.9 something. 1.91, somewhere around these values. But if you check out the module preferred choices, okay, you have 2 and 2.5 also. With this you are getting 1.19. Calculating again. Check it out. You can calculate and let me know if you get the same value. Okay. Or what we can do is to check out this slide over here. You can see that normal module here. Here the normal module is m cos beta. We can use this since the module is very low. Usually the module hovers around 3 to 3 and above. We just keep it. It's safe to keep it 3 and above. So let's use this. So m equal to m cos beta. Let's mn, that is normal module, equal to m cos beta. We'll use this before we go to the third step. Okay, let's just do that. This second step, and this is the third step, right? So we'll use this. Okay. So mn, this mn equal to m cos beta. So this is given in equation 12.19c. So let's use that. Okay, so that means module m equal to it is mn, that is 1.91 divided by cos 25 degrees. So this will give us value of 2.11. So we'll approximate this to 3. So m will keep it as 3. Okay, so this is the answer. Okay, module is 3. So once we have got the module, go back to the presentation here. We can use these values to get the parameter, but we'll find only few. So just like how we did for the Spurgear, we'll find only those values. Let's find only very few values. All are not required. That's enough. Okay, so these values are enough. So module we have got here as 3 mm and Z number of teeth. What is the number of teeth? Z1, Z2. We have found out. Yeah, 72 and 24. So this is 72 to 3 and 24 into 3. Okay. 22 into 3. So this will be 216 mm and this is 72 mm. Okay, so pitch diameter for pinion. Then let's do it for gear because we know gear is a weaker member, right? So this will be 72 into module 3 that we have already found out. This diameter is already found. Outside diameter is what 72 plus 2 into 3. This is 2 to 2. So that's it for step 3. So only the key dimensions are required. So sometimes they may ask uh, some dimensions in particular, but this will be in general. Right. So next step. So next step is here in case of helical, the dynamic load. Dynamic load and wear load are separate here. We can club them, no big difference. Okay, so this is dynamic load on gear tooth. Dynamic load. Okay, this is given by, I need to type this formula. If the version is available a little bit tight. But let's see how similar it is. Check K3V. We have K3V CB cos square beta. We need to add here cos square and beta. So this square goes up, cos square beta, and ft again cos square beta, cos beta. Side is side. This is just cos beta, and same thing in the denominator. Cos square and beta. Pitch dia. This is the pitch dia. Someone replying in the private chat. This itself is the pitch dia. D2 and D1 here is the pitch dia. I need to worry. This is FT. Yeah, I think we are set. Okay, but the equation is 12.26a. So this is 12.26a. Okay, yeah, this is for the dynamic load. So let's find out one by one. FT, a part of it we had done previously. We can use the same thing. This is FT. Here, let's use the generalized module for simplicity. Over Let's use this as 3 itself. Okay. 11920.53 over 3. 3973.51 will be in newtons. Okay, so one by one we are finding the parameters here. K3 I think already given in the just below the equation itself. K3, check it out the PPT. As this is 20.67, 20.67. Then C is error. We'll cover C later. Let's find B first. So B is this value. Let's put it here. So once you find the module, no, just update it. Whatever values, wherever you substitute, give it substitute it as the value of the module itself. Okay, so Mn will be 3 itself. So this is equal to, this will be into 3. Okay, that's B, and cos square beta we can do it later. Ft beta, then velocity V. So velocity V is, what is the velocity here? 1.51 mn into mn. So it's 1.51 into 3. I think we have covered all the values except C. So for C there is an entirely different procedure. Let's check it out. So same as that of the how we solved the Spurgeon. So for getting the value of C here, we need to check out which is what error we get. So for error, we need to refer to the next table, that is type of error according to the cut criteria. Where it is not given, and also you see there is no module 3 here. Okay, there is no module 3, so thereby it's a dilemma. So what do you do? What do you take the value of C? What we'll take, we'll take some value here itself, which is closer to 4. Closer to 4 itself, some value. We will not prolong this further. Just some value, whichever value is nearer here. Let's see. Error. We are designing with gear. Gear is cast steel. Cast steel and steel and steel. Steel and steel only. So steel and steel with error. Error we can choose. So let's choose industrial, or let's say precision. Some accurately cut gear for module. Accurately cut gear 0.0254. Let's go back. 0.0254. 0.025, somewhere in between here for steel and steel. So let's choose this here. So 330. Again, see for helical gears, you can approximately choose the value of dynamic factor. No need to interpolate, because as it is, this is a little bit lengthy compared to the spur gear. So what you can do, you can assume some value over here. So let's take 0.3 and 330.9. 330.9. You just say here, assuming error equals 0.3. 0.03 from table. This is 12.12. So in case of helical gas, you can assume and just write the value of C. Okay. Okay, let's calculate these values. 47.32 into 3 is 141.96, and velocity 1.51 into 3 is 4.53. Right. So now we have all the values. We can directly substitute in this equation here. Let's do that. So Ft is 3973.51 and Kv is 20.67 into velocity 4.53. So C is 330.9. Don't worry about the exact values. Okay, you can assume. We see this procedure. Okay, very less marks for the final answer. Okay. The number, let it be believable. That's quite enough. This is cos of 25. P again 3973.51. Again cos 5. And we have kV over here. Just copy paste. Then have C the cos square beta. And I think you can put the whole thing here. So the procedure matters, not the final answer. Okay, so calculate this and find the values. So meanwhile, I'll move to the next step. So FD, calculate using this set of formula given. So this is, we'll move on step 5. B, someone asking, B is already found. So if you check out step 2, no, if you check this step 2 in the Lewis equation, we have B already. So B we defined, which is given in the formula. To go back to the presentation, I'll show you. Yeah, this one. So B is given 12.23C in that equation. So this is given in 12.23C. So the same B we have taken. Okay, this B we have chosen and we just substituted it here. Okay, already previously in step 2 itself it is known. I hope this answers. And yeah, step 5. Go back to the PPT. Step 4 and this is helical, right? Oh yeah, I forgot to change this step 5. This is 5. This is the last step. Step 5. Note down this equation. This is D2. Okay, let's change this. Copy from the previous Spark here. Copy the whole thing. Okay, so this is D1B QK. We only need to input this and cos square beta. It's 12.26C. The equation is different. 12.26 in C. And this comes as a fraction. over is cos square beta. Cos square beta is over here. Cos square beta is cos square beta. Okay. So this again here it is d1 is written in the equation. You can see here d1 is written, but since the design is based on gear, right? So you can change that to d2. Okay. This we can change it to d2 because it is the design here is based on gear and not pinion. So this equals to we need to complete this. This should be greater than FD, greater than or equal to FD. We'll use the same thing. So D2 is this 72. Oh no, D2 is 216. 216 into B, I think we found 141.96. Then Q. Oh, we don't have Q yet. Okay, we'll post this later. So one by one we'll write down. So D2 D2 216 equal to 216 mm, and B is 141.96. Again, this is an mm. Then Q. So for Q, I think we need to refer here. Q is given in this fashion. Z2 by Z2 plus 1. I already input this. Yes. So this is equal to, say, 2 into Z2 216 divided by Z1. Z1 is 24. Right. Z2 is 72, not 216. 72, then 24 plus 72. Okay, this will give us Q, and K we need to find, beta we know. Right. So let's find this one. Anybody found out FD? You can calculate this entire thing and post it in the group chat. It's 2 into 72 divided by 4 plus 72. This is just 1.5. Right. I think we have all the values here. So let's just paste this. Let's copy the entire thing here. Okay. So this means D2 is 216 into B is 141.96 into Q is 1.5 into K, and we'll write this beta is 25 degrees as given in the question. And FD, anybody found out FD? FD, nobody here. Lazy afternoon. 67 to 4.53 into 30.9 into 141.96. cos of 25 square plus 3973.51 again into cos 25 negative cos 25 square 7 to 4.53 into 330.9 into 141.96 into cos 25 plus 3973.51 into cos 25. Let's see, cos 25 is good into 141.96 330.9 plus 51 into into cos 25 and into 8.53 into 0.67. Okay, so this is we'll break this up. It'll come into like 0.51 plus fraction. The numerator what I got is 361157.577. That's what I got in the numerator. Then the denominator you need to calculate. Just check out the numerator if I'm doing is correct. And cos 5 squared into 141.96 330.9 into 141.96 3.9 plus 3973.51 root plus 0.7 into 4.5. Okay, denominator I'm getting 300. So that means FD is 3136.11577 divided by 300 plus 3973.51. So I'm getting FD 16012.1 newtons. So check if you got the same answer while calculating. So that means this is 16012.1. So that means your K should be greater than what value? This into cos 25 square divided by 16 into 141.96 into 5 is 0.2859. Okay, your K should be greater than this much. Now we'll go back to the presentation. So check if you got some other answer. Let me know. Okay, so K value for 20 degrees and 0.2859, 0.2859, and combination is steel, steel. cast steel and carbon steel. So I think this is the closest value. The next highest is this value here, 0.40. So for that, the hardness for pinion is 200, gear is 150. So BHN for pinion. Let me type this. So based on this, BHN for pinion is 200, and that of gear is 1. Okay, that's it. That's the required answer. That is the hardness for both gear and pinion. Okay, this problem was a little bit different because two different materials were given, and you had to shortlist the gear for the weaker material, right? So we'll solve one more problem in the next class, that is on Monday, and we'll wind up with helical gears. Any doubts you have, you can ask at this point. We are done with the second numerical on helical gear. So tell me if you have got any different value somewhere. Okay, you can work on that. And keep note on the steps. Steps, the sequence has to be maintained. Both spur and helical, they are most frequently appearing on the tests. You may have an option like to spur helical gear or bevel and worm gear. So you may have an option between these two. Spur and helical, since they have same procedure, they're quite easier to remember and to do in the exams. Thus, we already solved 3 problems on spur gears and 3 more on helical. We'll cover by the next class, and should be good to go. So this will be almost a 20 marks problem in the exam. Okay, one problem itself will fetch you around 20 marks. And if you're fast enough, you can finish this in half an hour max. Right. So that's it for today's class.